Bond energies and bond length. Again with the energy business, right? We can use individual bond energies to estimate enthalpy changes of reactions. Back in chapter 6, we did a lot of stuff with the heat of reaction, right? Bond energies can let us estimate. This will be not as close as those calculations we did, but still it's helpful. So what is bond energy? Bond energy is the energy required to break 1 mole of the bond in the gas phase. And you might say, well, how can you have a mole of bonds? Well, it would be a mole of molecules breaking 1 bond in each molecule. Bond energies are always positive. It always requires energy to break the bond. They never just fall apart by themselves. If it makes the bond, you have to put energy into the molecule to break it. The more energy it takes to break the bond, the stronger the bond is. This makes sense. You know, I don't know if it has a name, but I think there was this game that kids used to play where you'd hold somebody's hand and somebody else would try to karate chop and break your grip, right? Yeah, so they don't let them play that anymore because you can break your wrist, right? No fun in elementary school. But the stronger your grip is, the more energy is needed to break that handshake. If we look at this hydrogen chloride, to break that into its individual atoms requires 431 kilojoules to break the hydrogen-chlorine bond in 1 mole of these molecules. Compounds that have stronger bonds tend to be more stable. They tend to be less reactive. In order for HCl to react, that bond has to be broken. It can't react without breaking the bond. Well, bond energies are going to be a little bit different in different compounds. If we look at a carbon-hydrogen bond, if we look at the carbon-hydrogen bond in methane, to break this 1 bond, a mole of those, is 438 kilojoules. If we look at trifluoromethane, where instead of 3 hydrogens on that carbon, we have 3 fluorines, but we're still breaking this carbon-hydrogen bond, it's 446. If that's bromine, it's 402. If it's chlorine, it's 401. So they're not exactly the same. So we use an average. So they measure these bond energies in a whole bunch of different compounds, and then they average them, and there's tables. The CRC is full of them, just pages and pages. So the average carbon-hydrogen bond energy is 414 kilojoules. Double and triple bonds have higher bond energies than single bonds. This makes sense. So if you're playing that, does that game have a name with the hands? No. Maybe we should make one up. I don't know. Break your wrist game. So if you're playing it and you're holding 2 hands with the other person, is it going to be harder to break through? Sure. And if you both grew an extra arm, right, and did it with 3, like a triple bond, it would take more. It just makes sense. Here's some bond energies. Let's just look at these carbon bonds, carbon-carbon bond. So here's a single bond, 349 kilojoules per mole, a double bond, 611 kilojoules per mole, a triple bond, 837 kilojoules per mole. The fact that this is sharing 6 electrons means that the bond is much stronger than if it's only sharing 2 electrons. So this table is in the chapter, and then there's also, I think in the appendix, there's an expanded table. There's one little odd thing in here. This carbon-oxygen double bond, the average bond energy is 736 kilojoules per mole, except in CO2. In CO2, it's 799. That's significantly higher, and CO2 is a very common reactant and product, and so they give it separately. So how do we use these bond energies to estimate enthalpy changes? Well, this is another application of Hess's law. What we do, let's look at this picture first. What we do is we imagine that we're taking our starting compounds and breaking their bonds. Here we're only breaking the ones that are needed. We need to break this chlorine-chlorine bond. We need to break one of these carbon-hydrogen bonds. And then we're putting them back together. When you break a bond, you have to put energy into the molecule. When a bond forms, that energy comes back out. Conservation of energy. You cannot make energy or destroy energy just by making bonds and breaking them. So what goes in comes out. So bonds breaking is endothermic, positive bond energy. Positive from the standpoint of the molecule. You're paying me, money's coming in, energy's coming in to break my bond. Bonds forming is exothermic, energy leaves. So to find or estimate the heat of reaction, we just add up all the bonds that are being broken and all the bonds that are being formed. So the sum of the bonds that are being broken, those are positive numbers. All the bonds being formed, those are going to be negative. Okay? We've talked about energy being stored in chemicals, right? The chemical energy. The bond is one way that energy is stored in a molecule. An energy-rich compound such as gasoline can undergo a reaction in which weak bonds are broken and strong bonds are formed. So you break the weak bonds, that requires an input of some energy, but strong bonds being formed releases a lot of energy. It's the forming of the chemical bonds that releases the energy. A potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. Well, let's start with the balanced chemical equation. So we're given the formula. So CH3OH, and it's combusting. What's the other reactant? O2. You can't burn stuff without oxygen. What are the products? CO2 and agua, H2O. So when hydrocarbons burn, compounds containing carbon, hydrogen, and possibly oxygen, they burn, they react with oxygen, they always form CO2 and H2O. And then we just have to balance the dumb thing. 1 carbon and 1 carbon. Total of 4 hydrogens, so we need to put a 2 over here to make 4 hydrogens. We've got 2 oxygens and 2 oxygens, and over here we've got 2 oxygens and 1 oxygen. Well, let's try increasing. Let's try doing 2 here. So then we need a 2 here. So the carbons are balanced. 2 times 4 is now 8 hydrogens. And so we need to change this to 4. But hopefully we got rid of our odd-even issue here. 2 times 2 is 4 oxygens and 4 oxygens, a total of 8 oxygens. And over here, we've got 2 and 2. We don't want to mess with this, so we want 2 plus 6. So we'll put a 6 here. Yes, we'll put a 3 there because we want 6. And 3 times 2 is 6. I was just testing you to see if you're actually paying attention. No, I wasn't. I was being dumb. Okay? Then we're supposed to estimate the enthalpy of combustion. We're going to estimate how much energy is released when this burns. A lot. Yeah, we need a little closer estimation than that. So there's 2 different ways to do this. You can look at just the bonds that are breaking and forming, or you can say, I don't want to keep track of that. I'm just going to break all the bonds and form all the bonds. Which one do you want to do? The second one, good. I think that's the most straightforward. The people who like the first one are not going to have problems anyway. Now, we kind of need to be able to draw Lewis structures here, because just looking at this formula, it's not immediately obvious what kind of bonds we have. Looking at O2, that's actually a double bond, but you might not recognize that if you don't draw the Lewis structures. So we need to think about Lewis structures. So I'm going to save a little time by just drawing them for you. So that's what methanol looks like. And oxygen looks like this. And then over here we have CO2. And we have H2O. So we're just going to break everything apart. Instead of taking the two Lego structures and taking a few blocks from this one and sticking it on that one, we're just going to take it all to loose blocks and then put them back together. So we have 2 moles of this molecule. So we have 3 carbon-hydrogen bonds. So we've got, oops, I'm going to do this maybe in a different color. We have 2 of these guys, and we've got, well, let's do a bracket there. We have 3 carbon-hydrogen bonds. And what other kinds of bonds do we have in there?
Carbon-oxygen.
We have a carbon-oxygen and an oxygen-hydrogen. We have 1 hydrogen-oxygen bond and 1 carbon-oxygen bond. The 2 on the outside of the brackets takes care of the fact that we have 2 moles of that. Everybody with me? You can see how this can get a little messy. Then in the oxygen, we have 3 oxygens, and in each of those molecules, what bond do we have? An oxygen-oxygen double bond. So those are the bonds that we're breaking. And then what kind of bonds are we making? I'm going to make this green. So we have 2 carbon dioxides. And each carbon dioxide, what kind of bonds are we making?
COC.
We've got 2 carbon-oxygen double bonds. So we've got 2 carbon-oxygen double bonds. And in water, there's 4 water molecules, and what's being made there? We have 2 oxygen-hydrogen bonds. Everybody okay with that?
How did you, I was looking at the CO, the plus the CO.
This one?
Yeah, I'm trying to figure that one out.
That's this bond right here.
Oh, okay.
So we've got carbon bonded to hydrogen, and then there's 3 of those, and we've got 1 carbon-oxygen single bond and 1 oxygen-hydrogen single bond. Any other questions? Now I need to go look up the bond energies for these guys. So first I'm going to look up carbon-hydrogen single bond. So carbon-hydrogen single bond, 414. So in here, 414. Is that positive or negative? It's positive. I have to put energy into the molecule to break its bonds. So all of these orange ones are going to be positive. All the green ones are going to be negative. Then I need a carbon-oxygen bond. Carbon-oxygen single bond, 360. And I need an oxygen-hydrogen single bond, hydrogen-oxygen, 464. And then I need oxygen-oxygen double bond. Okay, and there it is, oxygen-oxygen double bond, 498. Now, doing this on paper, you probably want to just copy it down, not erase like I'm doing, but I don't have enough space for that. And then over here, I need a carbon-oxygen double bond, and this is in CO2. 799. Yeah, I remember that one too for some reason. So that bond is 799. Is that positive or negative? That's negative. When bonds form, they release energy. And then I need an oxygen-hydrogen bond. Oh, we already had one of those. This oxygen-hydrogen bond, I think that was this last one, wasn't it? 464. Negative. Now it's a matter of a little bit of math. So I'm going to add these guys up and then multiply by 2. So 3 times 414 plus 360 plus 464 equals, and then we're going to multiply that by 2. And then I'm going to add 3 times 498. And just in case my calculator messes me up, because I forgot to bring my real one, over here now we have a total of 5,626 kilojoules. And then I'm going to, you can think of this as adding a negative number, or you can think of it as subtracting. So I'm going to add 2 times negative 799 times 2. And then I'm going to add 2 times negative 464 times 4. And I'm getting a total of minus 1282 kilojoules. Do we expect a negative number for the combustion of methanol? Burning things usually releases energy. So it releases energy. We expect that it's going to be negative. So delta H is negative 1282. This is for the reaction as written, right? Because we used all of these coefficients. So this is kilojoules for this reaction. But it's asking for kilojoules per mole. Per mole of what? Probably methanol. So if it's kilojoules per mole of methanol, this is the amount of energy that we get from burning 2 moles of methanol, right? So our final answer here, we're going to have to take that and divide it by 2 and say that it's negative 641 kilojoules per mole of methanol.
So the total of the CO2 and H2O is negative 1282?
This green at the bottom is all of them added together.
So we would take the 5626 plus what?
Plus 2 times 2 times negative 799. Plus 4 times 2 times minus 464. Any questions? You might say, well, that's a little tedious. Yeah. But lab can be a little tedious too, right? Can you imagine trying to do the experiment? You can do this and keep your hands dry. But the explosion would be fun. Yeah. So that's bond energy, and then we have to talk about bond length. Just like with the energy, the length we usually talk about an average. The average bond length is the average length of a bond between two particular atoms in a large number of compounds, because it's going to vary a little bit. But we do observe that double bonds are shorter than single bonds, and triple bonds are shorter than double bonds. So here, comparing single, double, and triple bonds between two carbon atoms, we see that the bond length of the triple bond is 120 picometers, double is 134, and the single is 154. And we see a correlation that this shorter bond is stronger, and the longer bond is weaker. That's a general trend, but there are exceptions. And you do not need to memorize bond strengths or bond lengths. There's a table of average bond lengths. And again, we see this pattern between single, double, and triple, that as you increase the number of bonds, that it becomes shorter.